YouTube, thanks for clicking on today's video. I'm going to start with some bad news, actually. There's an 80% chance that you haven't subscribed to the channel, and I don't know why, because all we get is positive feedback. It's growing. You're missing out. Why would you come over here, watch an amazing video, and then say, oh, I don't want any more amazing videos? Sub to the channel. Do it, please. Thank you. So welcome to part 3 of 3 Become a Data Scientist videos. So you'd think that the third part is the final part, you know, when I say that there's 3 parts, you'd probably think that. There might be, as a reward to the community and everybody. At 300 subscribers, we are doing a final project. That's right. If you want to see a culminating data science project where I go through, I use everything that I learned in the 3 hours. So I might look up some other functions, but aside from a couple functions, I'm just using all of the theory that was shown previously in the 3 hours, and including this one. Those are the tools that we need, so those are the tools that we're going to use. So if that's something you want to see, then please leave a like on this video, and most importantly, subscribe to the channel. You're missing out. Come on. So with that being said, today's video is on big data and Spark. So in the last video, we had pandas and NumPy, which is great. We also had Matplotlib for graph. They're all great libraries, except they rely on all of your data fitting into main memory on that computer that you're running. So if you're running it on Google Colab, maybe you have 4 gigs or 8 gigs on your own computer. Maybe you have 8 gigs or 16 gigs. Whatever it is, that's not that big of a number. If you think you're never going to surpass that, you will. You need Spark, big data solutions. So you're going to want to watch to the end of today's video. As with the others, if you haven't seen the first or second parts, I'll put them right up here. So enjoy today's video. I hope you like it. If you do, leave a thumbs up. Please subscribe to the channel so that we can get that 300 milestone. And don't just stop there if we're at 300. Keep going. Enjoy. Have a great day. Thank you. Bye-bye.
Last time we used pandas, and pandas is great. This lecture is not trying to show why pandas is obsolete, because it's not. It's extremely popular, and I also still use it every day. So just to be clear, we still use it. But there are circumstances when we run into problems and it is no longer the best choice. And that is when we have too much data, okay? Either too many numbers or too many big numbers, whatever it is. Our computer, which basically on a normal Colab, so last time we were using Colab. So basically let's treat this computer as a Google Colab node. So we were on our own PC, and then we were basically sending directions to Colab, okay, instruct. So our PC memory is fine. Like if we have 8 gigs of RAM, then maybe 1 gig, this is a way overestimate anyway, maybe 1 gig is using for us because we're just opening this browser and sending instructions to Colab. We're saying do this, and then it actually does it. So for example, we write like import NumPy. That goes over to Colab, and then it imports NumPy. Okay, it actually runs that. I'll just write np. Okay, so it imports NumPy, and if it has, say, 8 gigs of RAM, then maybe it's using, I don't know, 2 gigs now. It's still an overestimate, and these aren't actual numbers. The 8 gigs are actual numbers. What's being used is kind of random. And now maybe we tell it to read CSV. Okay, so instead of doing this, we actually tell it to read xyz.csv, where xyz is already somewhere on this machine, or it could download it and then try to open it. But what that does, when we read it, that puts it into main memory, and a lot of the time that's going to be fine. If it's not that big a file, it's going to go from 2 gigs to maybe 3 gigs, or 2 gigs to maybe 5 gigs. And sometimes we get 9 gigs, and it crashes as soon as it gets to some threshold where it's more memory than it can take. All right, it's not going to crash at 8. It'll probably crash at like 7 or something like that, because it's not going to devote all of its resources to this. But if it's too big, it will not open it. Pandas is not going to say, okay, I'll open half of it. It doesn't do that. Sure, you could split the file in half and then open half if that's what you wanted to do. And then if later you could open the other half. This is a problem. If you want to try and open your dataset, which is, you usually do. You spent all this time using SQL. So this was lecture 1 where we do SQL stuff. We try to pull in, or we try to create some table, and then we save it as a CSV. And then we try to read that CSV, and we can't. It's just too big. Okay, so what is the solution? Well, luckily we have something called Spark, which is absolutely amazing. Something that came first was actually Hadoop. I'm not going to bother talking about Hadoop too much. They actually intertwine nowadays. They are involved with each other. But I'm really only going to talk about Spark, which is performing these type of tasks like reading CSVs and performing calculations and transformations on them. They do that in main memory. Great, okay, so it's exactly the same as Pandas. Pandas is, I told you, it opens in main memory as well. It does, but Pandas has no concept of multiple computers and assigning tasks to different things. So in Spark, when we have this Google Colab thing, and we can use Spark and Google Colab. I'm going to show you after I go through the theory. Here we instruct, say, read CSV. Let's actually say that this is Spark and not Pandas now. Okay, so if we're running a Spark read CSV, what it does is it contacts all of its nodes, whatever you happen to have. Okay, so yes, maybe you still have 8 gig on this machine, but then if we try to read a CSV, it actually says, okay, no, I want to put some of it on this machine, number 1, put some on this machine, number 2, and some on this machine, number 3. And if these all have 8 gigs, and it was maybe a 9 gig file, then that's fine. You can open up 3 gigs on each, and then that would be your file. It'd be split apart. Okay, so this is like your CSV. Some of it's here, some of it's here, some of it's here. So if I was to really paint this in a picture, we would have some file that was colored like this. So maybe the first section was the red part, the section was the blue part, and this is rows and columns, so they're all just, each of them all have the same columns. They have different rows. So maybe that's the third part. And then maybe we actually do this. Okay, so we split apart the file. Now, that's good and bad. We did open it in main memory. The file is open here and here and here. So that's great. Now we actually managed to open the file. It's just split across 3 different machines' main memory. That's fine. What I've actually described here is what in Spark is called an RDD, and I'm not going to get too much into the Spark nonsense. This thing you have to understand. Resilient distributed dataset. So resilient because it's in main memory, distributed because it's on these 3 different machines, and dataset because, well, it was originally one dataset, and so it's a distributed dataset. So this is the fundamental Spark object. And when we use PySpark, which is just a abstraction to Spark, which was originally written in Scala.
Hi everyone. So if you made it this far into the video, I want to tell you I'm actually really proud of you, okay? I'm studying at the University of Waterloo in Ontario, Canada, to show you 2 things. One, that I learned a lot, and you should sub to the channel, because there I will gift you that content that it took me 5 years to learn, and I'll put that in little short little videos like this one, where you can learn everything you need. And 2, to show you that I've had my doubts here too. I know what you might be thinking, it's a lot of content, and that you're stressed out. Don't worry about it, okay? We all have our doubts, and we'll all push through. So, please sub to the channel, give the video a like for support, and I'll see you soon. Keep watching, okay? It's really important that you keep watching. I'll see you soon. Bye-bye.
PySpark is writing Python code to pretty much perform transformations on this RDD. So let's look at some examples. Okay, so suppose we had the following list of numbers. Okay, maybe we had this in a Python list. So this is in our driver program. This is where we're writing the code. Okay, so on the collab node where we're writing the actual code, we have maybe nums is equal to this thing. Now this is going to be our data set for the example. And notice that I explicitly wrote this list of numbers on the driver machine. So remember, where we're writing code, that's where the driver machine is. That's one computer that probably has, what, like 8 gigs of memory. So yes, this list fits in main memory on that single driver node. So why are we bothering to use Spark? Well, it's just, this is a contrived example, and if you were really doing things, then you would use a CSV, or reading from a file, rather than actually explicitly putting the stuff in memory, because that's a contradiction. If you can fit it in main memory on the machine, then you wouldn't bother to distribute in the first place. And for testing, what you can do in Spark is I can say parallelized, so I'll say pair nums, or nums in a parallelized way, is actually spark dot, I'm not going to write the spark dot, I'll just write the main stuff. It's going to be parallelize this list. Okay, and what that does is it's going to distribute this according to whatever nodes or worker nodes or machines we happen to have available. And let's just suppose that we have, say, 2 worker nodes available. This is going to be one of them in blue, as is going to be the other in red. Okay, so we have 2 worker nodes, and so when we run this part, this stores it in the driver node, so I'll keep that over here. This is where all this code stuff is actually being written. And then nums is actually going to be on the main memory of the driver machine. So it's on the driver. Then we have pair nums, so it's when we write parallelize the nums, that's when it says, okay, I actually want this object to be an RDD. Okay, so this is an RDD, this thing. And we're going to store that in pair nums. And what that does is it's going to distribute this onto our worker nodes. And so maybe we'd have 5, and I'm just kind of writing them in here, not with commas or how it would interpret it. I'm saying this is maybe how it would split out the numbers. It would maybe put 5, 7, 10 there, and then 12 and 14 on this one. Okay, so that's pair nums. And if we tried to print out pair nums right now, if on our driver program we wrote print pair nums, then that doesn't output much of anything. Okay, this would just output, say, like, it's an RDD, because it's not going to output the actual RDD, because this data is distributed across these machines. We don't have access to it. I'll show you later how we can grab that information. Okay, so now we have an RDD, and I'll just erase our print here. Now I'm going to show you some functions that we can do on this data. So first, maybe there's stuff there that we don't want. Okay, we want to remove some stuff, or equivalently, we only want to keep some stuff. So what we can do is called a filter. And that's the same idea as like a water filter. It's, keep the stuff you do want, discard what you don't. And to do that in Spark, we'd maybe write a new variable, and this is going to be an RDD. So we'll say even nums. If we want to keep the even numbers, then that would be equal to our previous, so some RDD. And then here we're assuming that the elements are numbers. Okay, we have to always keep in mind what our RDD actually is. So in this case, we know each element is a number, and so when I write .filter here, and I write this function, and I'll explain that in a second, this function takes one argument, which is the element. Okay, it takes in an element, and so this time it's going to be a number. Okay, and most of the time I'm just going to call it x, but right now, for clarity, it's a number. Okay, you have to keep in mind what it actually is. And now what this function is it's some sort of check which takes in an element, and it's going to return a true or false for if we want that element or not. So when we write this filter in our driver program, it's going to say, hey, I want you to filter on all of your elements. So you call filter on this one and on this one, and then that would actually remove it or keep it. Okay? So it's going to run this check that we do, and for our example, we say lambda num, which returns num mod 2 equals 0. So that would return true if the number is even and false if it's odd. Then what that would do is that we say filter on all of our different nodes. So all the driver does is it says, okay, you node do filter on all of your elements, and you do filter on all of your elements, and it keeps the things that pass the check, and it removes the things that don't pass the check. So for our example, when it calls it on these 3, 5, 7, 10, it first calls it for the 5, and so that's going to be false, so it removes that. It then calls it for the 7, false, it removes that, and then for 10, it keeps that. So our RDD got transformed into that on that node, and at the exact same time, that's why it's parallelized, this is also going on, where we have 12 and 14 in this one. Well, actually, we're going to keep 12 and 14 in that one. Okay, we're not removing anything. They're both even. Okay, so we just performed what's called a narrow operation on our RDD, which means, notice, these two didn't have to communicate at all, and we didn't have to talk to if there's any other machines. There wasn't anything else going on. Okay, the only communication was from the driver program to the nodes that said, hey, run this function on each of your elements, and keep it if you want to keep it, and don't if you don't. Notice the driver program, sure, it might contact it to make sure that it didn't run into any errors, but aside from that, it's not concerned with what's going on, and within each node, they're not concerned with what other nodes are doing. And that's going to be important for later, because some wide operations, which we're going to do, they require a lot of communication, and they are a lot slower, because we don't like network communication. Okay, nodes or machines talking to each other. Alright, we'll get more on that later. But for now, just picture that all we did is make the driver node tell each node to run a function on each of its elements, and they're not talking to each other. Okay? So anyways, now we have our even nums, and it's in an RDD. So again, just to be clear, if I tried to print even nums, it would not print 10, 12, 14, or any permutation of that, because the data is not on the program that has this code here. The data is on this machine and this machine. So if you printed even nums, it would again say, like, this is an RDD, okay? So if we remove that, there's another function that is extremely useful, which is not remove stuff or keep stuff. It says keep everything, but do something to everything. Do a one-to-one transformation. And so maybe we wanted to square each element. Okay, so we have even nums in this array. Then maybe we wanted to square all of the even numbers. And what we would get is another RDD. So maybe squared nums. If we set that equal to the previous RDD, so this thing, call its map function, map. So it's saying map what? Map a function to each of the elements. So this is also going to take a function. And if you aren't familiar with the lambda notation, sorry about before, it's just saying this is a function that takes in whatever parameter we describe here. So it takes in one argument, call it x, and this is what we return with the colon here. We return, for our example now, we're going to return x squared. Okay, so that would then say, okay, the driver program would run, and it's saying, okay, hey, you red machine, I want you to apply this function to all of your elements, and I want you to apply your function to all of your elements. And so at the same time, it's going to just produce, this will turn into 100, and this will turn into 144, and whatever the square is of 14, I actually don't know. And I'll just say 14 squared. Okay, so that would change that data to that. So that was another narrow operation where, notice, to call a function on each of the elements, we don't have to talk to any of the other nodes. Okay, so I think that's it for these very simple functions, these narrow operations. In the next section, we're going to go over wide operations, which are often necessary, but they're also a lot slower because it means we actually have to move data around. Because in these examples, we just had the data staying on the nodes. Okay, there's stuff here, there's stuff here. It's not moving between machines. But in wide operations coming up, we're going to have to do that. Sorry for the quick transition there. Maybe we want to get a count of each element. I'll say our answer, or what we want to see at the end, is going to look like we want 1, and then how many ones we have. So we have 2, and we have 2, so it'd actually be in a list like this, or in RDD. We want 1, 2, and then 2, and we have 1, 2, 3, 4 2s, and we'd have 3, and how many 3s we have? We have 2. Okay, so this is our end goal, is this thing. So right now, it's distributed something like this, where on this one machine, we have, say, 1, 2, 2, so that'd be the first 3 elements. Maybe they're on this machine, maybe on this one, we have 1, 2, 3, so that'd be these ones. And then on this machine, we have these 2 elements. Okay, the first thing we're going to do is apply a map, which we just learned about. So as key val pairs, that's what I'm going to call this. So we're converting these elements to key value pairs, where the key is whatever it is, and the value is 1. So we're going to take each element like this one, and this would be 2, 1, and this would be 2, 1. We want to do this mapping because then it's basically saying we have a 2, and then we have another 2. And I know that's confusing because we already have 2's there. Spark very commonly wants these key value pairs, where you do something like group by the key. We're going to do that soon. We rely on this key, and then we'll do something with the values. And so if the value is just 1, that's saying, hey, we have one of these things. And that'll make more sense shortly after we do the next step. So we're going to do this map that does that, and we do that with nums dot map. Map takes a function which takes 1 parameter. It's saying, what are we doing to each of them? I want to return the 2 tuple, so a tuple with 2 elements of whatever x was, and then 1. Okay, that's exactly what we just described. It would be itself, and then comma 1. Okay, x comma 1 for all of them. Let me show you exactly what this just did so we're crystal clear. So that was a 1, 2, 2, and now it's a 1, 1, and a 2, 1, and a 2, 1. And this is 1, 2, 3, which is now being converted to 1, 1, 2, 1, and 3, 1. And yellow is going to be 2, 1, and 3, 1. Okay, so that's the transformation we just did with the map. It's very quick. Now what we need to do is somehow combine the like keys. So we need this 1, 1 to be with this 1, 1. So then we'd have basically 1 and then the list of the values. That would be all the 1s, and then we could just do something to this list, and then so that would be summing it. For example, if we summed these values, then we'd be left with 1, 2. So let me show you that exact method the bad way. Okay, and it's very important to understand the bad way, because you may sometimes have to do the bad way, but this time I'm telling you, you don't have to do the bad way. But first of all, for explanation, let me show this the wrong way. And it's with doing what's called a GroupByKey in Spark. The wrong way is to do grouped, so set some variable equal to grouped, and that is equal to whatever we had before, so as key val pairs, so this RDD, and then we want to do a GroupByKey, and we don't need to give this thing any arguments. It just groups by the key, and then essentially what it doesn't exactly do this, but very, very close. It's then going to say to each of these machines, hey, I need you to group your keys. And to do that, they know which place to put their keys and key value pairs, but they know which machine here. So say that these are two other machines. Everyone knows based off of the key, and technically what we do is hash the key. It's just applying some function to the key to know, oh, okay, we actually wanted this machine, so we wanted this to go to 1 and this to go to 2. And it's the same function that across all of these three different machines. So each of these have, say, this function f, which hashes the key, and so it says, okay, element 1, you're the tuple 1, 1, your key is 1. I'm going to hash you, so I get f of 1. And what that does, it says, for example, it's going to bring it to this machine. It's going to put 1, 1 here. And then, for example, for the other key, for 2, it's actually going to push that over here. And so it does 2, 1, because the key is 2. And then the other one, 2, 1, well, it's the same function f that takes in a key. It's got to produce the same result. And so the things that I made up there are just what the hash function specifically did, as in which machine each key went to. The important part is that the hash function takes in a key, it looks at that key, and it says, okay, I know which machine to put this information to. And it's the same function across all of these different machines. So they all know where to put the stuff. And so now there's communication here as well, and all of the like keys are going to go here. So this is we hash 1, and so we send this information over. We hash 2 and 3. 2 we know goes there, and 3 I can just basically decide. As a user of this program, you wouldn't actually decide. It's just I have to decide as a lecturer where it's going to go, and I'll say it goes here. Okay. Let me give myself a little more room here. Okay, and now the last one I'll do quickly. It's just they both must go here, right? So we just did a lot of network communication, and keep that in mind. Okay, so there's communication there and here. We just did a lot of network communication. These potentially, machines 1 and 2, these are potentially completely different machines than blue, green, and yellow. There's a chance they're the same, but there's a big chance that they're actually different machines. And so we're pushing basically even more information than we started with. We started with 1, 2, 2, 1, 2, 3, 2, 3. And now we're pushing across the network 1, 1, 2, 1, 2, 1, 1, 1, and so on. Keep in mind that that's bad, but right now we don't see a different way. And so we're going to do this. We're going to push all of the information onto these other nodes or machines. And now what we can do is this machine will basically transform this thing. So now it has all its like keys and values. So then it would have a list of 1 and then 1, 1, because we're looking at the key, and then this is the list of values that we have. So now that we have this grouped information, what we can do is just apply a map, which instead of keeping the second argument, we want to apply a map to each of our elements, which are 2 tuples, where the first element is the key, and the second element is basically a list of 1s, where the number of 1s we have is the number of occurrences of that key, then what we can then do is simply apply a map which sums over that list. So we could then do answer, so it'll be the same as this one. Order possibly not the same. The order doesn't really matter right now. It's just we want a list of all of the distinct elements and their numbers and their counts. So answer would then be equal to grouped dot map lambda x, which returns, so x is a tuple right now, and so we want the tuple of x0, so the first thing, that's the key, and then we want the sum of the list, which is x1. Okay? This would absolutely produce this answer. So we grouped the information first. After we mapped this thing to a key value pairs, we grouped all of the information and then we summed that list. It might not be clear because we haven't talked about it yet, but there's a much better way to do this that's actually doing something very similar. But let me show you what is way faster if it's possible. And for this example, it happens to be possible. So we're still happy with our map. We're going to keep the key value pair idea. But we're instead of a GroupByKey, we're going to do what's called a ReduceByKey. So I want, and this will straight up be the answer. The answer is equal to the as key val pairs dot reduce by key. And now this will take a function, which is kind of confusing at first, but it makes sense. So it takes two parameters, and we're going to sum these two things. Now, that's not expected to make sense yet. I'm just writing it down so we can explain what this thing's doing as we go. So the first thing that it does is that group by operation, except what it doesn't do is pushes everything onto a different machine and then sums the information there. Okay, it actually does this group by and this reduce first. So let me show you what would happen with our example. We're still going to have this information. Okay, we have, right now we've mapped it, so we would have 1 1 and 2 1. And 3 1. Okay, so now what I can do is, if we're reducing by key, that means we're doing something to the values. So before we did a group by key, which just means, group all of the like keys, group all of the values to that same key. And now what we want to do is reduce by key. And so this means actually do something with the values. And so on each of these machines that the RDD is already stored on, it's actually going to first transform it into something like this, which is the same grouped information like before. So it would be this key, and then its list of stuff, which is just 1. And then it would map these to 2, and then 1 1. And that was no network transformation. We didn't have to push anything across the network because this is all done on that same machine. So we do that transformation. So these are gone. We first do that. And now similarly, we'll have 1 1 2 1 3 1. Okay, so it does all of that grouping operation. And now that we grouped it, we gave it this function that reduces by key. Okay, we said xy, and we do x plus y. So what that's referring to is, if we look at this example, it's actually going to transform this into a key value pair of 2, and then the summation of the elements of the values here. Okay, so it's going to do x plus y. If it was 1 1 1, it would produce 3. Right now we just have 1 1. That's going to produce 2. Okay, so we're summing them in this example. So this turns into 2, 2, and the other one turns into still 1, 1. And I know it might seem like an error to you that we have x plus y, like xy, and we only had one element in the list, so that's kind of confusing, but it works fine. Okay, so we do that for all of them. Okay, and I just did that quickly. Now what we do is the same thing as the group by. Okay, so this is exactly the same step from this point. So again, maybe we had our two machines. We had these other ones. And on this machine, it's going to get the 1 keys, and the other one's going to get the 2 and the 3 keys. So here, this guy is going to pass to this machine, it's 1, 1. And to the other one, it's going to be right here. It's going to get this 2, 2. And the green is going to get 1, 1 over here, and 2, 1, and 3, 1 here. And the yellow is going to push all the stuff over here. Okay, now that they're all on the same machine, we can do that same group by operation. And the huge step already happened here, okay? The huge improvement already happened because what we did, instead of passing over 1, 1, and then this was 2, 1, and then 2, 1, that's what we had in the other example because we didn't group this information here. That's why it's so much faster, because we have to transmit way less information. It's so much easier to say if we had 100 2s on the same machine, and in big data you're actually going to have like millions of them possibly. It's way easier to ship over the example of 2, 1 million rather than 2, 1, 2, 1, 2, 1, 2, 1 a million times. It's way easier. Okay? And I know that this example may not have illustrated that perfectly because all that we did is combine this 2, 2 that used to be a 2, 1 and a 2, 1. But if you really do upscale that to what it would be when you're really doing this, the performance is huge. And so if you can do ReduceByKey, you absolutely should. And so what it would do from there is, again, we're saying to ReduceByKey, so we don't have to explicitly ask for a sum later because we're already doing the sum here. It reduced on this machine that it was already at, and it's going to reduce here. So first what it's going to do is produce all of the groups basically. So it's going to group this information, and over here it would actually do 2 and then 1, 1 and a 2 in there, and then 3 and a 1 and a 1 in there. And again, we're actually asking it to do x plus y here. So it does reduce here, and it's going to reduce on the new machine that it transferred to as well. And so it would again produce our correct answer of, after summing those values, it's going to have 1, and there was 2 of them here, and over here, sorry for it being a little small here, we would transfer that into 2, 4, because we had 2 1s and 1 2, and we had 2 3s, and so it's 3 2, which is again our correct answer. Okay, so the moral is that if you can do ReduceByKey, this is how it works. It's going to reduce stuff on the machine that the RDD is already stored on, the machines that the RDD is already stored on. It's going to do all that reducing there, and then when it ships it over, it's only shipping over one value per one key. Before in a group by, we were sending over like 1 million values for the same key, but now it's just we reduced it on that machine and then send it over, which is way better because network communication is not good. It's really what slows us down. Okay, but you can't always do a ReduceByKey. There's some examples that I'm not going to go over that you might just want to group by key. Maybe your goal is to group the information and see these different values. You might want to know what they are. So in those cases, then you would just do a group by key, which is very expensive. Okay, ReduceByKey is also expensive, but it's a lot better than a group by key. Okay, now remember, what we're left over is still this RDD thing. So if I'm just to clear this up, we had on these two machines, this was machine 2, Okay, and sorry for the quick transformation there, but basically what I did is this was the result we had, is this RDD, and so basically I color coded this so that our answer is this part was in green and these parts are in yellow, meaning what machine they're actually on. Okay, and so it's still an RDD. It's still distributed in this thing. If I was to do print, and if we had this thing called answer, okay, so answer was blah blah blah, it's how we got there, rather with the ReduceByKey or the GroupByKey. The ReduceByKey is better. If we were to do print answer, okay, so on our driver machine or where we're writing our code, if we write print answer, then what that does, it outputs this thing. Okay, and I'm not showing you that it outputs the RDD. It literally says like, this is an RDD, because to that program, that's what that thing is. It's this abstraction, which is a resilient distributed data set. It's distributed. If you ask what it is, it's not going to give you its contents because they're not on that machine. They're distributed across these two. And so I've wishy-washy said you can look at the information, but you can't. You can't look at the information unless you explicitly ask for it, which a lot of the time is a scary thing to do. But what you can always do is take a small subset. Okay, so if this thing was really big, and at this point for our answer, we'd probably just collect all of our information because we did a huge reduce. We did a lot to get back a much smaller piece of information. But what we would do if it maybe is too big is we could do answer.take. So if we did answer.take2, what that would output is instead not RDD. This thing would output two of them. Okay, and I guess we'll say it takes the first two. The order is kind of weird, but it produces, say, one from this machine. So it would say we have 1, 2, and 2, 4. Okay, so we literally took two of the elements. It would output that for us because when we say take, it's saying, okay, I actually need some information from you and I need some from you. But this is okay because if we know we're only taking 2 or 5 or 10 or 50, then it's not going to crash our machine. Remember, we're distributing it because we're afraid that it will, and maybe we've tested already, that this too much information crashes our machine. But if we've distributed it, we can take some of it back after applying, and you'll probably do this for every time you write a function. You'll want to see if it did the thing that you wanted to do. So say you did some map and you weren't sure if it actually produced the even values. After you wrote that map, you could do whatever that variable you called it, .take5, and make sure that it actually did that. And now at the end here, we could actually try to do what's called a collect. So if we do not take2, but if we do answer.collect, that actually tries to bring back all of the information, and this might crash your machine. If you do .take5, that's not going to crash it unless you're taking something really nasty. .collect, regardless of how much you've done already, it may crash your machine because you're literally saying, hey, everything here, give me it, give me it, give me it, give me it. So what it would try to do is put this 1, 2 over there with that 2, 4 there. It would try to put this 3, 2 there. And this is all we have for this example, but so on. It would try to do everything. And if that's too much, then it would crash. And I have crashed many, many machines by doing collect. So that's all we're doing with RDDs. We're going to go on to the DataFrame object, which is basically using SQL in main memory.
Hi everyone. So if you made it this far into the video, I want to tell you I'm actually really proud of you, okay? I'm staying at the University of Waterloo in Ontario, Canada, to show you two things. One, that I learned a lot, and you should sub to the channel because there I will gift you that content that it took me 5 years to learn, and I'll put that in little short little videos like this one where you can learn everything you need. And two, to show you that I've had my doubts here too. I know what you might be thinking, it's a lot of content and that you're stressed out. Don't worry about it, okay? We all have our doubts and we'll all push through. So please sub to the channel, give the video a like for support, and I'll see you soon. Keep watching, okay? It's really important that you keep watching. I'll see you soon. Bye-bye.
In the first video, I talked about using SQL, and we haven't talked about it since. Didn't show you it in lecture 2 because we were assuming that you had everything in a CSV already, and you just pulled it into pandas, and that was great. Now this one, I'm saying, okay, maybe you have some CSV that is too big to load, and so you're going to actually use Spark to use this RDD thing. But now mixing them together, you may want to do basically SQL in PySpark. Okay? There's this thing called a DataFrame, which, yes, same name as a pandas DataFrame. They're different objects. You can have a pandas DataFrame and a PySpark DataFrame. And the difference is that a PySpark DataFrame is underneath an RDD. So maybe we had some table which had name and age and address. Okay, maybe you had this table which is a CSV. Okay, so we could open this up, and we could open it up into an RDD as well, except really what it is it's a table, and most CSV information is. It has some header, and then it has a bunch of identical looking data. And PySpark knows how common this is. It's like it came from an SQL table. It's just a standard table, except if you want to interact with this thing well, maybe sometimes you want to use an RDD, and that's fine. You can transfer between a data frame and an RDD fairly easily in PySpark. But sometimes there might be stuff you want to do knowing that there's column names. Okay, SQL is so great because this table has a column name and you know the type of that data. In RDD, it's good. It can be fine if you know what you're working with, but it's a lot easier if you already know that it's like, oh, okay, this is the name column and this is the age column and this is an address. I know that it's going to be a string and then maybe an integer and then a string. And so you can do so many wonderful things with this thing as a PySpark data frame. Okay, so I loaded up some CSV that had this information, and I loaded it into a PySpark data frame. Now there's some function called like read CSV, and that would read it into a data frame. And so this thing is just like a table in SQL or just like a pandas data frame, except it's distributed. So if this thing has 10 rows, or whatever I'm about to draw, if it has these rows, and I'll say this is a red one, red one, red one, blue one, blue one, blue one, blue one, blue one, blue one, green, 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 this thing is distributed. So maybe these are on a red node, and these are on a blue node, and these are on a green node. Okay, it is underneath an RDD, which really just means it is an RDD, except to you it's a data frame object, isn't it? You perform methods on a data frame, but underneath it's an RDD. So it's in memory. Okay, remember what an RDD is. They're so great because they're in memory, which means these operations will be fast. Okay, they will be fast. SQL tables are going to be stored on a hard disk, and it's going to be slow to read from that. Why we use pandas is because it works in memory. And if you can, you should use pandas because then it's all on the same computer. And as we just talked about with the group by and reduce operation, you want to do as little communication as possible. But if the data is so big, then the solution is to both have it in memory, but have it distributed onto different computers so that you can actually fit this data. And you can do any SQL that you want. You can basically write some SQL, and if you have this thing as a data frame, say it was stored as the object df, if df was maybe the read CSV, the read.csv of whatever this thing is. So just like ages, I don't know, people table, whatever it is. So we read that in, it distributed it, so it set up this thing. And now it's a data frame object with which underneath is an RDD. We can write SQL with this thing because it is tabular data, even though it's distributed. You can either do it in a way that exactly matches SQL, like you could write something like SQL and then pass the information that you want, like select blah blah blah. Okay, you can write stuff like that. Or if you have this data frame object, then there's similar commands for stuff like select. So if I wanted the age column, I could do select df.select age. Okay, and then maybe I wanted to group by the ages. Then I would write group by and then age. Okay, and so on. And there's stuff like aggregation for computing averages and all the same things that there are in SQL. You can either do it straight up by writing SQL syntax, or if you have this data frame object already, then you can do like .select, .groupBy, .orderBy, .limit, .distinct, all of these different things. All right, data frames are awesome because most data is structured and tabular in nature, at least the data that we really rely on in companies is like this. It's already in SQL tables, so we can manipulate it well in PySpark because it's Python. Okay, it's distributed, so it's in memory, it's very fast. We love the syntax, and if you wanted to convert this to an RDD, it's as simple as just, .rdd. If you want the RDD, you can actually do this. df.rdd returns this thing as an RDD, which isn't hard for it because it already is an RDD. It's just abstracting it into a data frame for you. And so we can do all of that awesome SQL stuff, except it's going to be faster because it's already in memory. And we can do all this fun Python stuff. Like we just convert it to an RDD, and you can do this map, this filter, all of this stuff. Python is just better than SQL. SQL is awesome for doing a lot of different things, but if you can get it into this format using PySpark, then that is better. And so you can save a new table, you can perform a bunch of transformations, you can save it as a new table, save it as a CSV, actually put it back on disk. So of course you might run into many circumstances where, remember, it is in memory. So if your cluster turns off, then you're not going to have access to your data anymore. So you will need to save it into CSVs again. Okay, and the only other thing I wanted to talk about with Spark is that, remember with these data frame things, I was saying that underneath they're really an RDD. It's true, you can access the RDD very easily because it is distributed. And right now I'm painting you this picture that you can see this name, age, and address column, except you might know the column names, except you don't know those actual row values. You can't view those unless you do, instead of .take, you would actually do display the df, and what that does is it produces a subset which you can look at. So that's all you need to know.